In this video, I'm going to give you an introduction to multiple linear regression. We want to start by giving you some idea of the general form of multiple linear regression, and that is we represent the y, the dependent variable, as a y with a y symbol. The betas are called the partial regression coefficients. The beta 1, beta 2, up to beta k are the slope coefficients, and the beta 0 represents a y-intercept. We're generally interested in getting the expected value, in estimating that expected value of y, which is the average value of y given the value of x that we get, the value of the x variables. This is called the deterministic portion because the average doesn't contain the error term. You can see that in the general form here we have a y value, and that is basically that deterministic function right here plus the error term. That error term is basically a random error. Note that these predictors can be the original variables, but they can also represent higher order terms. In other words, a squared value of a variable. When we plot a predictor against the response, then that regression is a simple linear regression, and it can be represented by a scatter plot that looks like this. If we have x and y, the scatter plot hopefully shows a linear relationship between the two variables, and we assume that these deviations from the line are normally distributed. But when you have more than one predictor, x1 and x2, then the relationship can be represented by a plane instead. And then the distance from each point to the plane is called the residuals. If the point is above the plane, then this is a positive residual. If the point is below the plane, then this is a negative residual. And if the point lies exactly on the plane, then that means that the residual is 0. The population model that we are interested in predicting is the expected value of y. And that's going to be only based on the deterministic portion. The estimate, we call it y hat. That estimate is estimating the expected value of y. And you can see that we put just tildes on top just to represent that these are estimates. Alternatively, we can call it B0, B1, and B2, and that represents the estimates of the betas. But still, we have these y hat is really what we are plotting here on that plane. So in other words, the plane is the prediction. Let me give you an example. Suppose you're trying to predict the price of grandfather clocks in an auction. You have age as a predictor and number of bidders as a predictor as well. So for example, this clock is 127 years of age, 13 bidders, and actually the price of that clock was sold for $1,235. So given this data, let's see what we get in a regression. Now, a multiple linear regression because we have more than one predictor. The x1 variable, let's represent age with x1 and number of bidders with x2 and price with the y variable. If you're going to read this data in R, you can use the read.csv function because it is a CSV file. You don't need the strings as factors is equal to true because we don't have any factor variables. In other words, categorical variables. Using the plot function on the dataset can give you a scatter plot matrix. The scatter plot matrix basically just plots all relationships at once. So for example, you can see that there is a relationship between the price of the clock, which is the y variable, and the age of the clock, which is one predictor. And this can be found exactly on the lower left part of the graph. You can find also the relationships between number of bidders and price, and also the relationship between age and number of bidders. Generally, the relationship between the predictors and the response, we want that relationship to be as strong as possible. In this particular graph, we can see that age and number of bidders, that relationship is, sort of not so strong, but it represents a positive relationship. So, for example, this age with price has a positive slope, which means that as age increases in the clock, then so does the price. The same thing happens with the number of bidders. So you want that relationships to be as strong as possible. But you don't want a relationship among the predictors to be strong. So in other words, you want this relationship to be as weak as possible. The output of a regression in R is shown here. So you can see the estimates. There is an estimate for every one of the slopes and an estimate for the y-intercept. The code to use in R is basically shown here in the call. Okay, so if you get that function, you don't really need to use formula is equal to, you can just put price. The tilde represents is expecting the predictor variables. And basically, if you run this line of code, you would get that regression output. You generally want to save this into an object. For example, you can call this object regression 1, and then you can say is equal to that regression equation right there, and then you get the output that looks like this using the summary function. So you can see that there's an estimate for the y-intercept, an estimate for the slope of age, and a slope for a number of bidders. Let's see how this relationship is represented in a scatter plot. In this case, is a plane. So you can see that there is an axis for age, predictor, an axis for number of bidders, a predictor, and then the axis for the y variable. We can represent this equation by the estimated price, or if you want to call it y hat, then that's fine. If you want to replace age with x1 and then number of bidders with x2, then that's probably shortens the equation more. The interpretation of the y-intercept is just the price of the clocks, the estimated price of the clock when age and number of bidders are equal to 0. We want to say that this is an estimated value always. For the slope, as age increases by 1 for the slope of age, then we estimate again the price of the clock to increase by 12.74, holding number of bidders constant. Or if you want to say considering the same number of bidders, then that's what we mean when we say holding the other predictor or predictors constant. Same with the number of bidders. As it increases, then we estimate the price of the clock to increase by 85.95, holding the age of the clock constant. In other words, considering clocks of the same age. We also have statistics like the RMSE value, which we can find under residual standard error. And what this means is this is an estimate of the error of the prediction. So we expect the error to be about, on average, $133.5. Is in the same units as the original problem. The degrees of freedom on the RMSE value is called the error degrees of freedom. And those degrees of freedom can be obtained by using n, number of observations, minus k, predictors, plus 1. The 1 comes from the y-intercept. Because we have 2 predictors plus the y-intercept, we are estimating 3 parameters. In that case, we got 29 degrees of freedom, and these are called the error degrees of freedom. The r-squared value is no longer a reliable estimate of the explained variation. We have to use now the adjusted r-squared, and we will explain why a little later. When we get an ANOVA function on the regression object that we saved, we get this output. The output contains a few things. We get the unexplained variation, the SSE. That value, the SSE value, is basically the sum of squared, sum of squared errors. The sum of squared errors is basically a measure of how good the model fit. So an error is y, the actual value, minus the predicted. And if we sum these errors and square them, then that's the SSE value. We want that value to be as low as possible. Similarly, the MSE value is the average unexplained variation. In other words, if we divide this SSE value by 29, then we get MSE. The two values work together. One is low, the other one is low. We also have SSR, which is the explained variation. You can see that this number, for example, for age, basically is large compared to SSE, so that means that there's more explained variation than unexplained in this case. And age is a strong predictor just because it represents, it gets a lot of the explained variation. Okay. Now, the number of beaters SSR, what that means is a little different than we would expect. What it really means in this output is the explained variation of number of beaters given that age is included. So it's an additional explained variation. So to summarize, we are trying to get the estimate of the expected value, and we do this by using the y-hat equation that gets us this plane that we get. The plane, we can visualize it if we have two predictors. If there's k predictors, then this plane is no longer going to be something that we can visualize as easy, but we can imagine it behaves similarly. The assumptions are the same. The mean of the error term is 0, constant variance of the error term, normality of the error term, and then independence of the error term as well. So we can check these assumptions by checking the residuals. So for example, to check if there's non-constant variance or non-linearity, we can plot the residuals against the predicted values. If we see some pattern like this, then that means that the data does not behave linearly. Similarly, we can check the normality of the residuals by using the QQ plot. Finally, we want to talk about linear models. We mentioned that the predictor variables can be quadratic values, in other words, squared terms. And this is still a linear model, because what it means to be a linear model, what we need is that the parameters are linear. In other words, we don't have any squared parameters, any square root of the parameters, or it's not dividing something. As long as this is true, then this is called a linear model. The predictors can have squared roots or something like that, or be squared and still be a linear model. So this model, although if we plot it, it would look like this. If we had the relationship of these variables, basically the prediction would look like that. That is shaped like the plane is just tilting, it is still considered a linear model. And the last thing to mention is that the highest exponent of any predictor variable is called the order of the model. So in this case, this is a quadratic model.